ยัง What's the problem? Maybe it's from another. Wait, just check it from here. I think you didn't show your account. Yeah. No, there is no. I think maybe yes, this one. No, too. Oh, what's the problem? Oh, Yes, sir, it's 3. iPhone 2, iPhone 1. Okay, save. It's no category is education. Category is education. Category is education. Category is education. Yes, sir. And look at this. There you go. This one. iPhone 2. Oh no. Okay, all right. Yes. Okay. 1 hour 20. Right? It's gonna be 21 and 12. Okay. So good evening. This is the first compensation for the mixing lecture of SCI33206, which is physics number 5, right? For the SK school, right? Okay. I hope the sound is fine. Okay. We are live at the atomic models. In we have discussed the Rutherford model, and there was a defect. Okay. There was an issue that the Rutherford model cannot well predict the behavior of light emission in terms of wavelength or spectrum or frequency, right? Okay, an electron should spiral toward the nucleus, okay, according to the idea proposed by Rutherford, and it should also emit a continuous spectrum, okay, because with this continuous movement, okay, going into the nucleus, okay, going into the nucleus in continuous spectrum would take place for the EM radiation, and gradually lowers its energy, okay, when it reaches when the electron reaches the nucleus, okay. That's the planetary Rutherford model, okay. According to a classical electrodynamic theory, okay, it's something about charge and movement of electric charge. The frequency of the emitted electromagnetic waves should equal the frequency of revolution of the electrons in their orbits. Okay, and as the electrons radiated energy, their angular velocities would change continuously, and they would emit a continuous spectrum, right? Yeah, that's the defect by the Rutherford model, and some further developments to atomic models will be explored later, okay. And what does the continuous spectrum mean? It means a mixture of all frequencies, okay, not the light spectrum as actually observed, okay. However, the Rutherford model of the atom give us way to that of Niels Bohr, okay. Actually there should be X. Oh, this is GAF, okay, it's fine. Which explained the characteristic radiation emitted from the atom, okay, the Niels Bohr atoms. Okay, anyway, that's the first former generations of the atomic model, right? Yeah, as you can see, the defects in the Rutherford model, many people, okay, again, when you work as a physicist, you would be able to remember basic theory in physics, right? And yeah, various phenomena, including the electromagnetic radiation emitted by a heated object, which is known as black body radiation. This is gonna be discussed later. The emission of electrons by illuminated metals, known as the photoelectric effect, and the emission of sharp spectral lines by gas atoms in an electric discharge tube. This is also photoelectric experiments. Okay, you will see it later, and could not be understood under the classical physics. Okay, the people who works in physics, which are called physicists. Okay, they can remember the classical physics, but they could not use the theory of classical physics to explain all of these. Okay, and yeah, black body Okay, let's start with the first phenomenon which could not be well explained by the classical physics. Okay, black body is an ideal system that absorbs all radiation incident on it. Okay, as the light enters the cavity through a small opening hole, part of the light is reflected and part of the light is absorbed on each reflection from the interior walls. After many reflections, essentially all the incident ray is absorbed, okay, after several times of reflection. Well, you can take a look at this, okay, at this figure. Here is it's like a sphere, okay, but it's a hollow sphere, okay. Actually, it can have any kind of geometric shape, okay, not wholly sphere. But for simplicity, okay, they just draw it like a sphere. A good approximation of the black body is a small hole, okay, small hole here leading to the inside of a hollow object. Okay, and you can see the blue line here, which blue straight line, which represents the ray of the light. Again, when the light hits the internal part of the black body, okay, there should be some reflection, right? Okay, they got reflected, they get reflected, and here this is the second point where we could find reflection, the third point, fourth point, fifth point, and blah blah blah. Okay, and finally there will be no light at all from this single light. Okay, and yeah, thermal radiation originates from accelerated charged particle, okay, near the surface of an object. The radiation emitted through the small hole leading to the cavity depends only on the temperature of the cavity walls and not on the material composition of the object. Okay, it depends on the temperature here. Okay, temperature of these wall, of these curvy walls, but that doesn't depend on the material composition of the object, its shape, other factors. Okay, the light emission will depend only on the temperature inside this black body. Okay, as the temperature of the black body increases, the total amount of energy area under the curve it emits increases. Okay, as the temperature of the black body increases, the total amount of energy under this curve, okay, increases. As you can see here, the 4000 curve would have a higher energy, because this is the if you make the integration, right, you would get the energy of that experiment. For example, this is light, but working at 4000 kilometer. I don't know how you could find 4000. It's a very very high temperature, high weather. Okay, yeah, when you reduce the temperature, you get something like 3000 Kelvin. Okay, and the area under the blue curve will be less than the area under the curve by this one. Okay, in the green one, which uses only 2000 Kelvin, you can see here that the area under the green curve is smaller than, much smaller than the 3000 Kelvin curve and the 4000 Kelvin curve. Okay, this is from experimental data of a black body radiation with respect to the classical theory. Okay, here is the wavelength that human eyes can see, right? The relationship between the wavelength at which the curve is maximum is called lambda max. Okay, is denoted by the Greek alphabet lambda with the subscript max. Okay, max stands for the maximum wavelength. Okay, when the curve is has the greatest amount of area. Okay, you get the greatest area, you have lambda max, and the absolute temperature of the object emitting the radiation too, right? It depends on two factors. Okay, lambda max and absolute temperature. Okay, it doesn't depend on the shape, the geometric shape of the object at all. Okay, it is known as Wien's displacement law. Okay, this displacement law states that the product between the maximum wavelength, okay, the maximum wavelength with the maximum value of wavelength where the curve is maximal, just multiply it by t, you will get this constant. Okay, and I would not give you a proof. Okay, you can go to any other books to get into the detail of this expression. Anyway, let's talk about the first problem. Okay, from a star observation, if the wavelength corresponding to the maximum in the intensity versus wavelength curve is 2.3 × 10⁻⁷ meter. Okay, what should its temperature be? Okay, this is the maximum, okay, intensity with respect to the wavelength curve. Okay, so what we could do is that we should get back to this figure and this figure too, right? Yep. The maximum in the intensity versus wavelength curve is this value. So the peak, okay, the peak of the curve at this situation is very, very tiny. Yeah, if the wavelength corresponding to the maximum in the intensity versus wavelength curve is 2.3 × 10⁻⁷ meter, what should its temperature be? So we need to use this expression, okay, which is the Wien's displacement law. Okay, if you want to find t, you just move lambda max to the right hand side and you get 0.289 times 10⁻⁻² and divided by lambda max, right? Then lambda max is this value, okay, 2.3 times 10⁻⁷, and yeah, if you convert it directly, you would get somehow like 100,000. Okay, in yeah, let's make the division of this one. You would get 0. Blah blah blah. Okay, which is 0.1257. But nowadays he is 1.257 times 10 to 4 Kelvin, which is a very high temperature, high value of temperature. Okay, let's go further. If you have any questions, just let me know. As usual, in 1900, Max Planck developed a formula for black body radiation that completely agrees with experiments at our wavelength. Okay, if you work in electrical engineering, you have to know